So hello, we are Group D, and today we are pitching a cybersecurity solution that redefines trust in autonomous aviation. Our focus is zero trust architecture for securing UAV systems, making sure only authorized users can access UTM services. Each of us analyzed a different piece of this problem, from threat modeling to zero trust requirements, and together we've built a solution that strengthens the safety, security, and mission assurance across connected airspaces.
Um, Hello everybody. So here's a quick overview of what we'll be presenting today. We'll start off by explaining the problem and our motivation, then we'll walk through our threat analysis and system requirements. Okay. Uh, so we'll walk through our threat analysis and system requirements. From there, we'll introduce our proposed solution and highlight the entrepreneurial value of this approach. And finally, we'll end with our conclusion summarizing our key findings and the overall impact of adopting zero trust in UTM environments. Next slide.
So, starting off with our problem statement, as UAV adoption accelerates across commercial and public domains, so does the need to enhance the security of UTM functional blocks. From an operational perspective, unauthorized access undermines compliance with aviation regulations. It results in the loss of critical information and causes flight disruptions. These factors can lead to monetary loss, reputational damage of an organization, and threats to public safety as well. From a technical perspective, traditional access models rely on predefined roles and attributes, and they lack continuous verification, leaving these services vulnerable to various threats. However, if we implement a zero trust architecture, we eliminate implicit trust by enforcing continuous verification and least privilege principles. There currently lies a strong barrier for the scalability of UTM adoption, which is the security of the drones and the services that they provide. With modern AI powered adversaries invalidating the outdated perimeter security models, and without strong identity and access controls, UTMs will not be able to scale to national drone delivery, emergency response, and other commercial and private uses. For example, a compromised USS node could disrupt thousands of flights within seconds, bringing large monetary losses and reputational damage. However, by implementing our proposed zero trust architecture with continuous verification and least privilege principles, we can greatly improve the scalability of UTMs in our public and private sectors going forward.
So the challenge of securing UAVs is a direct application of foundational cybersecurity engineering principles such as security, safety, and resilience. These core security principles are addressed through the proposed zero trust architecture, which discards the outdated perimeter-based trust models in favor of the new never trust, always verify methodology. This constant verification is designed to prevent unauthorized access and data breaches. This security posture also protects physical safety, as a cyber attack that compromises a UAV system could have catastrophic real-world consequences, such as jeopardizing flight safety, risking physical damage, or creating hazards to human safety. To maintain this state of security and safety, the system must be resilient, a quality enhanced by our zero trust architecture. By integrating proactive defense mechanisms such as continuous monitoring, real-world threat detection and response can be achieved. Microsegmentation contains the impact of a breach by limiting an attacker's lateral movement ability through a network. So like in this sort of integrated approach ensures that the UAV system is not only secure by design and safe in operation, but also resilient enough to function in a modern security environment. Next, so one of the largest challenges, as I went over, currently facing modern UTM systems is an overall subpar security design. This neglect to security carries with it a multitude of risks resulting from potential compromise, including but not limited to business critical data loss, asset loss, mission failure, as well as the associated legal, monetary, and reputational damages associated with any one of these outcomes occurring. The fact that current UTM systems unfortunately leave these challenges unaddressed creates an immense barrier to extracting the full value of modern UTM technology within the field, meaning lots of unrealized gains. By adopting a zero trust architecture-based security, we can largely mitigate these risks, allowing stakeholders to safely adopt UAVs at scale and enjoy the benefits that come from this.
So with these current UTM security strategies, there are numerous gaps in the currently applied systems that can be turned into really great opportunities. So current systems utilize static credentials, where we instead can implement real-time dynamic credential services. Without this continuous verification, there's nothing stopping a malicious user to take over a session and deploy high-risk commands, in which case a continuous trust engine will stop that threat. There's weak telemetry protection in UTM systems, which can be solved by ensuring secure telemetry pipelines for the USS and the ATC. Long-lived sessions prove to be another weakness, as an actor can spend numerous sessions without having to re-verify who they are, whereas a limited session security engine will ensure smaller session times. And there will be limited to no tamper evident logs. There becomes an opportunity to create an immutable audit logging service to create a record log that can be used in reports. These gaps that are in current systems show that the private companies, defense systems, and state agencies are still using ad hoc security, prioritizing immediate functionality over long-term resilience. This opens the door for our standardized zero trust architecture framework to secure the entire UTM ecosystem.
Our threat model looks at how attackers break into UTM-connected UAV operations by targeting several weaknesses. The primary threats include command spoofing and credential theft, where attackers impersonate legitimate UAVs, operators, or entities. Data manipulation is another major threat, where GPS, telemetry, and flight plans can be altered mid-mission. We also face information disclosure, where attackers intercept credentials or missions data. Denial of service attacks can overwhelm UTM or USS servers, breaking availability, and privilege escalation lets attackers gain elevated permissions. Finally, repudiation becomes a problem when no logs exist, and it allows attackers to deny malicious activity. All of these show why current models fail and why continuous verification is critical for UTM security.
Now onto the attack surfaces. These attacks enter through multiple weak and unmonitored surfaces across the UTM ecosystem. The first major attack surface is authentication points, where spoofed identities, stolen operator credentials, or weak session keys allow adversaries to pose as legitimate entities. The second attack surface is data exchange channels, which include telemetry streams, GPS signals, flight plan uploads, and mission data transfers. If these channels are unencrypted or poorly protected, attackers can manipulate or intercept the data in real time. The third surface is database and core systems, where weak access controls allow tampering with flight data, operator information, and authorization rules. Lastly, the fourth attack surface is a system performance layer, where attackers can flood UTM or USS services with requests leading to miscommunication and potential flight disruption. Essentially, every weak identity check, unencrypted link, and exposed API becomes an entry point for adversaries. All of these threats directly impact the most critical UTM modules. Access control services is a first point of failure because spoofing, credential theft, and privilege escalation break identity, trust, and authorization decisions across the network. The flight planning module is also highly vulnerable since attackers can tamper with routes, alter the flight data, and cause deconfliction, which increases collision risk. Next, the data exchange module handles communication between UAVs, USS operators, and air traffic control, and those can suffer from interception or alteration of mission data. Finally, flight operations and navigation systems are also affected when GPS or telemetry spoofing leads to misleading drone behavior and unsafe flight plans. Collectively, these compromised modules weaken the integrity, availability, and overall mission safety of the UTM environment. Here, all of the UTM threats are mapped using the STRIDE framework. Spoofing would occur when attackers impersonate the UAVs, operators, or USS entities. We can mitigate this with TLS 1.3 and X.509 certificates to prove identity. Tampering targets flight plan, telemetry, or GPS, and we can prevent this using HMAC, SHA-256, and AES-256 to ensure integrity and confidentiality. Repudiation becomes a problem when there are no audit trails, so we can use immutable digitally signed logs to mitigate this. Information disclosure exposes credentials, flight plans, and all other flight data, and we can address this using TLS 1.3 in transit, as well as AES 256 storage encryption and zero trust to enforce authentication at every point. Denial of service attacks overload UTM or USS systems with requests, so we can apply rate limiting and ML based anomaly detection. Finally, privilege escalation allows attackers to gain unauthorized access, so we enforce zero trust and short-lived JWT tokens to ensure continuous verification. Together, these stride categories tell us where UTM is vulnerable and shows how ZTA closes every gap.
So here I mapped all the UTM privacy threats using the Linden framework. Linkability is when attackers can watch the use space activity and look at for timestamps or authorizations and start linking it back to a specific operator. This can be handled by rotating operator identities and limiting how much identifying data each service can see. Identifiability goes a step further, where attackers can correlate metadata or logs to reveal who the operator actually is. This can be prevented using pseudo-anonymization, continuous verification, and strong encryption on all identifiers. Non-repudiation issues show up when someone can change a U plan without leaving a trace, and this can be fixed with digital signatures, tamper-evident logs, and strict version control. Detectability is when attackers monitor things like RF activity and can tell when a UAV is taking off or landing, and this can be reduced by encrypting telemetry and minimizing metadata that can give away flight statuses. Information disclosure happens when there's weak authentication and it can expose sensitive flight plan data. This can be mitigated through secure coding practices, input validation, strong encryption, and then zero trust access controls. Unawareness is simply operators not knowing what data is collected and how it's being used, and this can be addressed by giving clear privacy notices and letting operators view or revoke their consent. Non-compliance comes up when organizations fail to notify operators after a breach. This can be avoided through regular audits and consistent documentation to ensure quick and accurate notifications.
So here's our diagram for our proposed architecture. This solution has numerous zero trust aspects, most notably being identity and access management, multi-factor authentication, short-lived tokens, least privilege, a continuous trust engine, real-time session evaluation, and an audit logging and compliance. So this is the top half of our diagram. This contains the secure access layer to the UTM system. This layer configures identity and access management through the use of public key infrastructure, authenticating any actor utilizing the UTM portal. When logging on, users must pass the multi-factor challenge, which will ensure their identity while accessing the UTM layer. The authorization server will then push short-lived tokens while defining the different permissions for the user, meaning different users will have different access to different services on the UTM services chart. This can be seen by many of the line associations coming from the actors. We can see this more looking into the bottom half of our diagram. So looking at the bottom half, we have the UTM services. We can see those limited permissions in place. For example, a security analyst would have no reason to manage flight plans like a drone operator would. So by not allowing them access to this service, we mitigate the risk of privilege escalation or lateral movement. Throughout any one session with the UTM service, a continuous trust engine will be ran, which logs users' data such as IP addresses and behavior. It will also monitor sessions, prompting for reauthorizations for any high-risk behaviors. This data is then logged to ensure proper compliance and post-event checks in the case something were to happen, kind of acting like a paper trail for the cyber team.
So our zero trust architecture provides a continuously verified access to all UTM services, and every request is validated. And this eliminates spoofing, tampering, privilege escalation, and insider threats as well. And on this particular solution slide, we are introducing the core zero trust architecture that governs access to UTM services. And we applied strong cybersecurity and privacy principles, such as continuous authentication, least privilege enforcement, and micro-segmentation as well, so that each UTM functional block remains isolated and protected. And from a stakeholder perspective, Zero Trust directly benefits UAV operators by reducing emission disruptions, and it supports UTM administrators by lowering insider and credential reuse risks. And it also helps regulators meet aviation security requirements. The architecture is not only secure, but it also is technically and economically feasible. Next slide.
Now let's discuss the entrepreneurial side, specifically what does the CTA mean for market and investors. So it provides a unique value to all key stakeholders. For UAV operators and providers, our CTA offers non-disruptive security The continuous monitoring happens silently in the background, ensuring mission controls are protected without hindering flight operations, which is essential for rapid organizational adoption. For aviation regulators and authorities, we provide proactive auditable threat visibility. The immutable audit logs and continuous monitoring give regulators a high degree of visibility and accountability required to satisfy safety standards. This assurance of safety and accountability builds public trust, which is the single most important factor for accelerating UAV technology adoption across the defense and commercial sectors. Also, once the FAA mandates identity-centric continuous verification for UTM, every operator will need to use this model. So the UTM market is new, so whatever ZTA approach becomes the standard will establish a long-term competitive advantage. To prove this return on investment and feasibility, our validation plan uses two complementary methods. The first is a security simulation. So this delivers quantitative technical proof where we will use a software stress test to provide hard data on two metrics. First is unauthorized access denial rate, which shows how effectively we stop threats like spoofing and elevation of privilege. The mean containment time measures in seconds how quickly the system detects malicious command injection and instantly cuts off the attacker's session, proving the system's resilience. The second method is a high fidelity mockup. This is our visual proof of value. We will demonstrate the UTM administrator dashboard. This interface displays real-time risk scores for every active UAV. We can visually trigger a threat scenario where flight profile suddenly changes and shows the system instantly isolating the UAV's access. This demonstration confirms that our ZTA is not only secure, but is also easy to adopt and operationally superior. In summary, ZTA is the essential solution for the future of secure UTMs.
Um, so on this slide, there's supposed to be a video, but I guess we're having some technical issues with the volume. So I'm just gonna speak as the video go on. Please bear with us. So the zero trust UAV security demo that we are showing right now was implemented in Python. We use libraries like Pandas, NumPy, and the Matplot Python library to simulate the drone authentication events, and these also visually measured attacks reduction, and Panda data frames were used to generate and store authentication logs. Um, you can see some of these events going on the screen. For example, on this screen, we have the simulation live attack stream going on. And to the right of the screen, you can see the request button that a user can use to control some of these operations. And when you click on the run simulation button, it shows you a live result of the simulation, and stakeholders can really learn a lot from these event logs. And essentially, we've created a multi-tab UI to demonstrate the effectiveness of ZT and UTM environments. And on the next is our dashboard that shows our risk reduction graph. And you can see how ZTA is compared to legacy systems. Using legacy systems, you can see that attack success was really high, and legacy systems are like the CASA mode, old security systems that were in place. These were not very effective, but implementing our ZTA approach, you can see that attack success was greatly diminished. And the same applies to containment and false positives. And we also represented this on a 24-hour threat timeline. And then on the next tab, you can see that an operator ID is essentially required for, and with the right operator ID, a user can easily log in and you see a continuous verification that goes on in progress. And all this also helps to limit insider threats, since the correct IDs would always be requested. And then on the next tab, you see the compliance events, where you see the recent audits and some of the benefits of ZT as well. And on this, our goal was to put everything on a live mapping And you can see some of the UAV fleets that are in observation. The green fleets are very compliant, and those not so compliant are depicted on red. And to the right of the screen, you can see some of the interactiveness that goes on. You can get specific information on each fleet. And this is a live geolocation tracking, and it's very useful in UAV environments to essentially demonstrate security and demonstrate the effectiveness of our solution. So that's the demo. Thank you for listening.
To conclude our presentation, we see that the single biggest barrier that's currently holding back UAVs from large-scale growth is the insecure access to the UTM services that the UAVs provide. And to counteract this barrier, we have introduced a zero trust architecture that holds no assumptions, no implicit trust, and it just has continuous and provable verification. We're reframing UTM security as a way of growth rather than just a defensive shield. When these operations are secure, we unlock commercial expansion, higher traffic volumes, and automated flight capabilities, which at the moment are not possible in the landscape. The demand is already aligned. Regulators, operators, and service providers are all asking for the same outcome, which is trustable autonomy at a scalable level. The solution that we've built is available to expand across multi-operator and multi-agency UTM networks, which allows different stakeholders to operate coherently with each other in a secure environment without exposing themselves to risks. The opportunity is in front of us. We don't want to solely solve a cybersecurity issue. We rather want to enable a future in aerospace economy. Thank you for listening to our presentation and pitch.